I would like to welcome you to this lecture about the transformations towards sustainable energy futures and sustainable energy systems. I think that this is one of the major challenges facing the humanity, but perhaps also one of the largest opportunities to achieve sustainable futures. Let me try to illustrate to you by giving you just one example. If you look at the next half a century, what might happen, the global global economic output might increase on the order of 3 times or more. And if we provide the energy services such as lighting, mobility, heating, air conditioning in the same way as we do today, in that case, the emissions will increase at least 3-fold, leading to massive climate change. I estimate that the temperature increase would be on the order of about 4 degrees Celsius on average globally, but we would have also other pressures on the planetary system, such as a loss of biodiversity, acidification of oceans, and so on. So let me start this lecture by trying to set up the frame before I talk about the future, say a few words about the historical development of the energy system so that you can see what the momentum is and where we might be going. The first observation I would like to make is that the Industrial Revolution has catapulted humanity to incredible level of prosperity and production over the last 200 years. So many people can not only afford the basic needs, but can also live in quite an affluence. Unfortunately, it has also led to enormous inequality in the world. To give you an example, the global economic output per capita is on the order of $12,000 today in the world, which you would think should be enough for minimum needs that one would require, and perhaps even more. But on the order of about 2.6 billion people cook with solid fuels. It is estimated that leads to about 4 million premature deaths due to the adverse health impacts of indoor and outdoor air pollution. That is many times more than the death toll of malaria, for example. But also 2.6 billion people do not have access to safe sanitation, and about 2.6 billion people live below $2 a day. And that is about 40% of the global population that is now about 7.1 billion people. Now, on top of it, in addition to inequality, there are many unintended consequences of this development. And I've mentioned climate change, but pressures on our social and environmental systems and transcending what one considers to be safe planetary boundaries. Now, I will argue that to overcome these challenges and reap the opportunities of sustainable development, we need to transform the energy systems. Another word would be to say we need a revolution in the way we provide energy services. Let me try to illustrate that to you by about 2 or 3 pictures, what the challenge is. What you see here is the luminosity of Earth. It's a synthetic picture. We are looking at the Earth from the space. What you can see on your right are the nighttime lights of Japan. On the left, very bright lights of Europe, and in between a filament of light connecting Eurasia. And then toward the bottom of the picture, you see India emerging, very strong lights of India and China. Now, lights are, interestingly enough, a good proxy or a good estimate of where the economic activities are and where the people are who live in the affluence. So the dark areas mean that either nobody lives there, or these are the people who are excluded, the 2.6 billion who do not have access to modern energy services. It is estimated that about 1.5 billion people do not have access to electricity at all. Now, but this also illustrates, as I mentioned before, this an enormous economic output. Since the beginning of the Industrial Revolution, it has increased about 100-fold the economic output. But the darker side of this development can be more clearly seen if we turn the planet and look at it from the North Pole. You also see toward the bottom the incredibly bright lights of the North America. But if we look at the North Pole, this is a picture made about 20, 30 years ago. It no longer looks like this. The ice on the North Pole has disappeared, and let me just show this to you much more explicitly. The small yellow line shows where the ice was about 30 years ago, and you see where it is now, opening the sailing route, access to resources, and in some ways providing a positive feedback, accelerating the global change that is occurring. So this is one of the major challenges, how to achieve further development, connect the 2.6 billion or so that are not connected to benefiting from the affluence of the rest of us, and at the same time, not transcend the planetary boundaries. Now, let me try to just give you another illustration before I go to more substantive part of my talk. You see here the nighttime lights of North America. And I would like you to consider trying to guess what is in that little square toward the top of the graph. What is so bright out there? Well, this is one of the revolutions within the energy revolution. It's the so-called Shale Gas Revolution. Those little lights there, those bright lights is the so-called Bacon field where shale gas is being produced. Much of the gas is flared, and that's why it's so luminous. There are about 1,500 wells producing gas over there. You can see that those lights are even brighter than the urban center toward the bottom of the graph on the Minneapolis side pole, indicating how much energy we are wasting. But at the same time, it is a huge revolution because in the United States, gas prices are low. Gas has been substituting coal. And here in Europe, we have almost the opposite situation. We are subsidizing renewables, and they're making great inroads into the energy system. But at the same time, relatively high gas prices mean that coal is substituting gas in Europe and thereby increasing the emissions. So you see both in opportunities and challenges in some of those developments. Now, what I will, in the rest of my talk, I will base much of my comments on the global energy assessment that was completed a year ago, with about 300 authors and experts all over the world and 200 anonymous reviewers. You can, from this picture of the report, you can see it's a relatively thick book, too heavy to carry around, but published by Cambridge University Press, and it's available through usual bookstores. However, you can also download it from the website globalenergyassessment.org. So what I would like to show you is some of the insights of how this energy transformation might look like over the coming decades. So what are the key challenges we are facing? Number one, and I've mentioned that, is a lack of access, that 2.6 billion people have to cook with solid fuels and suffer all of the damages of the indoor air pollution, and about 1.5 billion people do not have access to electricity at all. Another issue that's facing every nation and region in the world is how to enhance the energy security, because energy is absolutely central for development. Let me just mention two more challenges. Air pollution, avoiding air pollution at the industrial scale, at the regional scale, and avoiding climate change. And what we did in the global energy assessment, and that's what I would like to focus on, is we set ourselves a number of normative goals of how to achieve this transformation in the long run. One of them is provide universal access to energy services within the next 2 decades or so in the world, stabilize climate change at 2 degrees Celsius, avoid air pollution related to energy, and enhance significantly the security of the energy systems. So let me first just illustrate to you what it means not to have not to have access to electricity. This is a picture from a village that has no access to power. One of the small-scale businesses is to go around with a generator set and charge up the mobile phones. As you might know, everybody in the world has a mobile phone. As yet, as I've mentioned, 1.5 billion do not have access to electricity. Now, really the negative aspect of this is, besides that it's a small enterprise creating economic activities, the really negative part is that the poorest people of the poor pay absolutely the highest prices for electricity. If you calculate what this costs, it's on the order of 10 times as much than you pay for electricity. Let's say on the order of $20, $30 per kilowatt hour rather than 10, 20, 30 cents, what one pays in the countries that have been electrified. Another example, cooking with solid fuels. On the left, you see a woman in Sierra Leone. She's pregnant and is carrying a huge load of wood. So indoor air pollution is both a health hazard for women and children who spend time mostly at home, but also have to spend lots of time gathering water and fuel wood. On the right, you see an open hut where it's being cooked with solid fuels, and you can see how many fumes there are. It's almost intuitive that this is an incredible hazard on human health. Now, the good news is, and that's what I want to share with you next, is that we in fact know how to solve this problem. And in the global energy assessment, we estimate that it would take on the order of $60 billion per year to solve that problem, but in addition to that, stable institutions, transfer and development and diffusion of appropriate technologies, and so on. What you can see on this graph is the percentage of people who have access to electricity, or how electrified the country has been. One of the first countries to electrify was United States, and you can see that they went from about 30% electrification to 100% electrification in the time period of about 3 decades. Mexico, China, Brazil are the next examples that have electrified more recently, have almost 100% access to electricity, and that also occurred within 2 to 3 decades. And then we see India and Sub-Saharan Africa, where the challenge is the biggest of providing access. The current situation is that about 2/3 of the people have access to electricity, but it's still 1/3 to go. There are massive programs to achieve that, and I think I'm very hopeful that that will happen. Now, if we look at South Asia and Sub-Saharan Africa, the progress has been relatively slow, with the order of less than 1/3 or just over 1/3 of the people having access to electricity. And in the global energy assessment, we assume that the development has to follow the upper, almost vertical curves to electrify within the next 20 years. And as I mentioned, that would take on the order of about 60 billion per year, a problem that's solvable, assuming that the right institutional and financial flows are guaranteed to those countries. Now, the question that one might ask, is there enough energy to provide for the 2.6 billion people who are excluded today, another 2 who will join the planet over the next half a century? As I mentioned before, today we have 1 billion people in the world. By the mid-century, there would be about 9, meaning global population would increase by 2. Meaning that we would have to connect about 4.5 billion altogether, roughly the same number of people who benefit from energy today. So the question is there enough energy sources? And I would like to show this to you in a little bit unconventional way. I will show you how much energy there is in terms of carbon that's locked into it, or rather how much emissions would occur if we consume or if we use all of those energy resources and reserves that are available. So first 2 numbers for comparison. Our current atmosphere contains about 800 billion tons of carbon, or petagrams of carbon as the scientists express that. So 800 billion tons of carbon. Before we started the process of industrialization 200 years ago, the atmosphere had on the order of 500 billion tons of carbon. So we have increased the carbon content of the atmosphere by about 300 billion tons, and it is estimated that that has already led to the climate change with a warming on the order of about 0.8 degrees Celsius on average. Now, we have emitted on the order of 500 billion tons to produce this larger storage of carbon, in quotes, into the atmosphere. About half of the carbon that we have emitted has stayed in the atmosphere. The other half has gone to the oceans and to the biosphere. Now, in comparison to that, if you look at the conventional reserves of oil and gas, and if you add the upper 2 numbers, 240 and 280 billion tons, you end up at about 500. So you can see it's on the order of what we have emitted over the whole history is what we could emit just from the conventional oil and gas reserves that are today economic and are reachable by current technologies. In comparison to that, the biomass above the ground contains also on the order of 500, up to 500 billion tons of carbon. Tar sands, slightly less than that, a huge, but unfortunately quite a dirty and difficult energy source. And then the mini revolution I was talking about, unconventional gas, including shale gas, it's really not known. All of these numbers are not known with very high precision, but might have on the order of 3 to 4 times as much carbon as in the atmosphere, and certainly exceeds by at least that much amount the conventional oil and gas reserves. So there's a huge amount of energy. Now, the return to coal is always a possibility there because many developing nations have huge amount of coal. India, China, just to mention 2, but also South Africa. And the order of magnitude is 10,000 billion tons. So coal is a resource that from the environmental and planetary perspective can only provide a part of the energy because of its very, very high carbon intensity. Now, let me contrast to that how much carbon we can emit if we want to stabilize global climate change at about 2 degrees Celsius above the pre-industrial levels by the end of the century. Well, another 500 billion tons on the order of that magnitude. That means we cannot afford to consume more than known reserves of oil and gas. Going beyond that and maintaining this climate goal of 2 degrees means that some of the carbon would have to be removed through so-called carbon capture and storage technologies and not vented in the atmosphere. Now, a number of studies indicate that the potential storage is quite significant, on the order of 400 to 1,500 billion tons. So in principle, we could consume more if we can deploy and diffuse the carbon capture and storage technology safely and in an affordable manner. The proof of that is still outstanding because we have a number of pilot plants around the world, but no true gigantic commercial facility. And then last but not least, another enormous resource are the so-called gas hydrates. And as you can see, they might contain on the order of 28,000 billion tons of carbon. Let me just show you how that looks like. These are the gas hydrates that have been drilled from the bottom of the ocean. You can see it's actually ice and snow. This is why Russians call that the burning ice. It's huge amount of energy, but here we do not have the technologies how to extract gas in a commercial sense. At the same time, gas hydrates are a potential threat if the global warming continues, because in the permafrost region there is also lots of methane locked in this kind of gas hydrates that might be melted and are already melting today in the area of the North Siberia and North Alaska. Now, let me come to try to illustrate to you how this transformation to a more sustainable energy systems of the future might look like. What you see here is the history of the global energy development. Today, we need about 500 exajoules of energy. To illustrate to you in the physical units what that means, corresponds to about 12 billion tons of oil equivalent. And 80% of that is fossil, as you can see. The expansion of gas, oil, and coal has been very, very random and very, very rapid. And the biomass has, throughout the period of the last 150 years, provided a very important share. And this is the main energy source for the people who have to cook with solid fuels. Now, here is one possibility of the future that fulfills these normative goals I talked about: 2 degrees, universal access, improving energy security, and eliminating air pollution. The first thing to observe is the gray region in the figure. The gray region shows how much energy we would have to save, either through more rational use or to much more efficient energy technologies in order to achieve this transformation to a sustainable future. How much we would save compared to doing the business with the current systems and current technologies. It's on the order of 40% in this scenario. Now, this scenario is quite challenging. As you see, there is on the order of 55% of renewables already over the next 2 decades, from 80% today fossil to 55% renewables in just 2 decades. That's a really tall order. Another potential concern is a relatively large amount of biomass, perhaps transcending what might be sustainable. However, this is a very, very stringent scenario, a scenario that will be very difficult to reach. It's one where carbon capture and storage and nuclear energy are assumed not to be successful in the future, and that we walk away from those energy sources. And this future would then not be possible if we do not achieve more stringent energy efficiency improvements as shown. Let me show you a second case out of 40 that we have studied in the global energy assessment. By comparison, I'll go back and forth so you can see the difference. Here we have significantly less renewables, on the order of about 30% over the next 2 decades, but much more gas, and nuclear plays an important role, as well as carbon capture and storage. Let me just briefly observe that natural gas combines very well with the renewables, because it's a kind of a virtual storage. When there is no wind or no sunlight, one can fire up the gas turbines and provide the electricity that might be needed. However, in this scenario, because there is considerably less renewables, we need carbon capture and storage from biomass, from coal and natural gas. And the carbon capture and storage in conjunction with biomass is a very special technology, because it would result in de facto net negative emissions. The way to imagine that is when we burn biomass and remove and store the carbon, there are no emissions, and then when the biomass regrows, it would absorb carbon from the atmosphere, creating a kind of a negative pump, removing carbon from the atmosphere. Now, what would be required to achieve these kind of futures? Well, vigorous improvements of technologies. And here you can see the trends, cost trends of technologies expressed in dollars per kilowatt installed capacity. Let me just show you that the trend is continuous, of ever declining costs. On the horizontal scale, you have the global installed capacity of those technologies. So as the capacity increases on the horizontal scale, the costs decline on the order of about 30% per doubling of the global capacity. And that is the case for a range of technologies, from consumer technologies, such as heating systems and so on, all the way to power plants. However, there are some exceptions. Let me just show you one that looks like a hockey stick, where the costs are actually increasing with the expanded deployment. That is the experience of nuclear in France and United States. And this is what we cannot afford to achieve this kind of sustainable futures I was talking about. We have to have improvements in all of the technologies. Now, what this curve shows is a gradual improvement. As you can see, the top curve, the yellow one, next to the top red curve, indicates the cost reductions of the photovoltaics. They have been on the order of almost 1,000 times over the last, since the technology was deployed over the last 30, 40 years. Now, so this is one mechanism. The second mechanism I would just like to briefly illustrate to you before I come to conclusion, and that is, from time to time, there is also a radical change in the technologies. There is a substitution of the old ways of doing things by the new ways of doing things, and those provide the major leaps in improving the efficiency and reducing the environmental impacts of technologies on all scales. So the first row shows you railways, second, flying machines, third one, communication, from letter to the most modern communication systems, then the automobiles, and last but not least, industrial production. Now, just to show you how radical these innovations have been in the past, in the periods of 50 years, look at the flying machines about 900. Those were the first aeroplanes that could fly. But just a decade before, some of the most famous scientists in the world were saying heavier than air flying machines would not be possible. And yet 50 years later, in 1950s, we were flying around the world. And today, almost every spot on this planet is reachable by aircraft. If you look at the personal mobility, going from horse carriage to the automobile from 1850 to 900 was another of those incredible revolutions that has led to the oil and the automobile and the petroleum development paradigm. Now, we don't know what the future will bring. That's the biggest uncertainty about the future, and that's why we look at so many future possibilities. I've shown you 2 scenarios, and I've included here a number of pictures that might illustrate that even by the middle of the century, the transport, communication infrastructures might look radically different from today. At the bottom of the graph are the industrial machines that can replicate themselves and reconstruct themselves. So a truly evolutionary idea that might be really evolutionary changes. But the emphasis is really on the systems, not on the individual technologies, in my view. And that's one of the biggest challenges. So let me come to the conclusion by showing you how a future energy system might look like. This is a particularly visionary one proposed from colleagues in Algeria. The idea here is because Sahara and Sahel regions are not just dry, but they're also even further drying up. So water is a major challenge and energy is a major challenge in this area. So the idea is to solve both problems at the same time. To take the water from Mediterranean and fill the dried lakes. These are these blue spots that you see throughout Sahara. Fill them up with the water and install solar thermal power plants to desalinate the water, produce electricity, and on top of it, tap into some of the smaller gas fields that are available there that are not commercial for connecting to the pipeline, but would be viable to connect to this new kind of infrastructures. Many of you have heard about the desert tech. That's the idea of actually producing energy in North Africa and sending it to Europe. I personally prefer this because it's producing energy and bringing it south to where the people live who do not have access to electricity and to the modern cooking fuels. So let me come now to the conclusion. What I would like to illustrate to you very, very briefly here, and that's, I think, the biggest challenge in achieving the opportunities of this energy transformation, is the investment. So at the bottom of this table, you can see the total investments, and the 3 rows show the investments of efficiency, renewables, and access, providing access to energy for those who are excluded today. So the first column shows the current R&D efforts, that's research and development in those areas, altogether about 50 billion, 2/3 in the private sector, 1/3 from the public sector, and as you can see, minuscule amount going to the access issues. So in some ways, it's not surprising that we have not resolved this issue. Now, the next column to the right shows what would be called early market formation, early deployment of technologies. That is where the biggest cost reductions that I've shown you in 2 figures ago, the biggest cost reductions can occur. So these investments are really vital. They're about 3 times as large and still very, very small for the access, but significant already for the renewables, relatively small for the efficiency across the scales. The third column shows the current investments, about 1,250 billion per year we invest in energy. And to the right, a range of what we would need to do to achieve the kind of sustainable futures I was talking about. The bottom line is we would have to increase the investments by 50% to perhaps double them per year over the next coming decades. Now, that's a difference of about 500 billion to over 1,000 billion a year. Curiously enough, we give every year 500 billion to subsidize fossil fuels, to a large extent in the developing countries, actually blocking this kind of transformation that we are talking. So we have to change the direction of investment, but what is more important is also change the nature of investment. Currently, quite a lot of investment is in, relatively piecemeal parts of the energy system. We have to take a view of the holistic view of the energy system, and many of the investments that are implied by the scenarios I was talking about would require quite high upfront costs. That means relatively high investments upfront and relatively low cost in the long run, so that there would be a kind of an investment in a sustainable future that might come in the coming decades. However, the current investment climate and investment regimes do not favor this kind of shift in the investment patterns. That's one of the greater challenges. The opportunities that this offers I've already mentioned: great business opportunities, improving energy security, avoiding dangerous climate change, and avoiding indoor and outdoor pollution. So I would like to come to the conclusion of this lecture. Thank you very much for your attention.